Hi, Alex.
Hey, Alan, it's Alex Sharp from TE. Can you hear me?
I can now, yeah. Welcome
Great.
aboard.
Thank you.
Morning, Nat. Are you going to be presenting, Alex?
Yes. Yes, I will.
Great, thank you.
How big's the typical crowd, Alan?
On this, on the Interconnect dedicated call, it varies. Maybe 6. We have more
Okay.
like 16 on the main call, but we've got quite a few. There's like 20 people that come and go, and we missed one a
Okay.
couple. So I was hoping that we'd get a. I've done a bit of work, so I was hoping that, and I did let everybody know, so I was hoping that we might get a few more today.
Okay. It's a good
It,
size.
it usually takes a couple of minutes for people to join, so hopefully we'll get some more.
Yep. Well, I know that Terry and Alan from TE should both be joining.
Okay, great.
Oh, and one other thing I thought of, Alan, was if you can point me to like an OCP PowerPoint template that's kind of standard or approved, I'd be happy to take what I brought today, which unfortunately isn't on that, and move it over and upload it or whatever is typically done?
Good question. I we have standard templates for the conferences, but to be honest, I just use my own one for these meetings.
Oh, okay.
Yeah,
I'm not
I don't think it's too strict in that sense.
okay. Well, I'm not going to say no to doing less work.
That's right. Yeah, we don't want people to unnecessarily
Yeah.
do this. So, hello, Alan Butcher. Are you from TE as well? Or,
Yes, I'm from TE too. Hi.
hi. And hi, Scott. So, Scott, this is your first time from Lopes, right?
Yes, I'm sitting in for Howard.
Ah, good. Okay, so Howard can't make it today.
Right.
Okay. Welcome aboard. And Terry. Hi, Terry.
Good morning, Alan. Good morning, everyone.
It's a shame. Hopefully, we normally get a bunch of people from Amphenol and. So, Scott, there's no one else from Lopes coming. I know that Howard copied a load of people.
No, I think it's just me.
Okay. There we go. Hey, Z. Hi, Z. Okay, we'll give it one more minute. All right. I think we can get going. Good morning, all. This is the OCP HPCM Interconnect workstream. So hopefully you all saw my note yesterday, where I've done a little bit more work. I'm actually presenting at the OCP Regional Summit, and I'm doing a little bit more of a dive into our thermal and the interconnect, universal interconnect we've been discussing. So I've done a bit more work myself to try and convey what we mean by universal interconnect. So I've got some updates to show you guys shortly. And I think we've been, just to bring everybody up to speed, we've been discussing the New Frontiers proposal that's still on hold, to my knowledge, in terms of getting words into that. We've got some basic startings in there, but nothing too much detail. And I was wondering, depending on how long it gets delayed, whether we could gradually work towards a bit more of a meat onto a spec. And from my regional summit, I was going to try and put a few more words into that section as well, so that the labs, Oak Ridge National Labs, can sort of see the potential, what we are thinking along this, what a universal interconnect could do for the industry, and especially in our HPCM format. So I'm making steady progress on that, and I think things are looking interesting. I think going in the right direction. I don't see any major challenges at the moment based on everybody's input. But I did go to OFC a couple of weeks ago down in San Diego, and bumped into the TE folk. So thank you guys, all from TE. There's 3 of you here. I did discover they're a little thermal interconnect that they've built for QSFP cages. And obviously we've been looking for how do we thermally mate as we plug in these E3 modules or the cables that are active cables. We want a thermal mate to the water chassis. And so what I saw from TE was, I thought, could be an interesting option for us. And so I know the TE guys, you're all new, so you're probably a little bit blind, but if we can start with you just giving us a quick overview, and then I can dive into some 3D models that I've been playing with and show, and hopefully it'll become a bit clearer where you fit in to our thought process here, or you could fit in is a potential option. So is that okay? So Alex, would you like to
Yes,
kick off?
happy to do that. Let me share my screen.
I guess we've got a few newbies. I guess the new people that are on the call ought to just say just a few words, just say hi and your affiliation and what you do.
Okay. So Alex Scharf, I've been with TE 28 years. I'm an engineering manager. I've managed teams from signal integrity to EMC compliance, as well as thermal teams. And so during my tenure as an engineering manager with the thermal team, Alan, who's also on the call, and I'll let him introduce afterwards, developed this thermal bridge product that we're going to present today. and I'll give everyone an overview just so we're all on the same page about what it is and how it solves thermal solutions.
Be great.
I'm located East Coast in Harrisburg, Pennsylvania.
Okay. Alan, would you like a quick introduction, and Terry?
Sure. Yeah, I'm Alan Bucher, I'm a mechanical engineer responsible for mechanical and thermal design and simulation. I also work with Alex in Harrisburg, Pennsylvania, responsible for TE Thermal Bridge.
Thank you.
Good morning, everyone. My name is Terry, and I'm based in San Jose, California. I am the product manager currently assigned to the thermal bridge technology for the high-speed I/O components, along with all the TE's QSFP family I/O products, connector and cages included.
Well, seeing we're a small group, maybe the rest of us would be a quick intro. Oh, and Scott, you're new as well. So Scott, would you like to introduce yourself?
Yeah, sure. Sorry. I'm Scott Shuey. I work for Loads as one of their industry standards coverage people. The backup Howard, who's apparently out on vacation or somewhere right now. And I know most of the people on the call here because I've worked with the TE folks when I worked at TE.
Okay, great. And Nat, would you like to do it? And then Z?
Yes, my name is Nat Nguyen. I am with IR Labs. We are working on silicon photonic-based optical chiplets, and we also had a booth at OFC last week.
Yes, I did see you guys actually. And Z? We can't hear you. If you're on mute if you're talking, Z. Maybe he's not at his desk. Okay, and I'm Alan. So I've been the technical lead for the OCP HPC sub-project for 3 years now. My background, I'm a double E, and I'm known as a pioneer in the FPGA computing world. And so, but I've become a systems engineer over the years and worked on high performance computing. And so I'm the one that's been bringing these radical ideas, and we've been all together refining them over in purely a concept to date. So that's what I've been up to. Okay, so fire away then, Alex. Let's.
Okay. Can you confirm that you can see my screen and it looks
Yes.
good?
Yes.
Okay, perfect. Okay, so thermal bridge. So the first thing, well, let's see, there we go. So I'm going to assume that everyone on the call is somewhat familiar with thermal pads, right? You've got some kind of heat source, a chip, a module, whatever, and you've got a cooling solution, and you need to bridge a gap between the two, and that gap may be a fixed distance. It may vary as a function of temperature or time or tolerance, whatever. And you need something spongy that's got some resiliency to it or compression to fill the gap and transfer the heat from the heat source to the cooling solution. And thermal pads have essentially been that solution for decades, if not longer. And we've all sort of know how to use them, and they're well proliferated, but they also come with a series of, I'll say, annoyances or challenges that we all just live with. And I'm going to highlight that a little bit and talk about how Thermal Bridge as a product, addresses a lot of those issues. First being thermal performance, right? Thermal pads are typically some sort of non-conductive dielectric filled with a conductive filler in order to get good thermal properties. It's typically like a silicone or something impregnated with carbon or metal particles. And so inherently, the base material is not conductive. And so thermal performance isn't great for the most part. Now you can get, the more and more you impregnate the materials with conductive fillers, you can get higher and higher thermal conductivity, but you're usually trading off mechanical properties, sometimes cost, in order to get to a good performing thermal pad, and then you start venturing into the putties or the greases or things like that don't really have a lot of mechanical properties to them. or certainly not a compressive property that you're looking for. Also reliability, thermal pads are, by the nature of their materials, they tend to take a set, right? When you compress them, they're not really wear resistant. They're soft, spongy materials, and even their compression will relax over time. And then lastly, in order to get the performance, the desired performance out of thermal pads, you have to compress them, and their performance is a function of compression, right? The more you compress them, the better they get, but then the more force it takes. And so there's this sort of trade-offs that system engineers are always making in terms of, what thermal pads am I choosing to get both right thermal and mechanical properties, and how much compression do I want to get the material versus, how complex and that compression system has to be, et cetera, et cetera. So thermal bridge addresses basically all of these points. And so let me tell you what thermal bridge is. So thermal bridge is a heat spreader or a bridge, as the name implies, that replaces what we traditionally think of as a thermal pad. It's made up of metallic plates that are interleaved, and we use a large number of highly parallel plates to achieve good thermal performance. And these plates are then integrated with a mechanical spring that allows compressibility so that you can compress like a sponge, but in this case, it's a metallic spring between your heat source and your cooling solution. And all of the plates within it can independently compress. And my favorite picture is up in the right-hand corner, where we've taken two sort of round objects and we're looking at the thermal bridge head on. And you can see all the individual plates that are in it and how the plates all individually compress or conform around the surface that it is mated against. And so a typical thermal bridge has about 1 millimeter of plate compression, where, thermal pads, depending on what it is, you have a fairly tightly toleranced set of working range of compression. Here, it's 1 millimeter. What you'll see as well is that the thermal performance does not vary as a function, or I guess technically barely varies as a function of compression of the bridge. So it doesn't matter if you compress it a little bit or a lot, as long as you have good contact surfaces, you'll get the same excellent thermal performance out of the thermal bridge. The bridge itself is dry, right? There's no lubricants or grease or anything in it in order to achieve the performance. But in many applications, a thermal grease can be applied to the surfaces to get even better performance between the bridge and whatever it's mated against. The bridge is completely metal, 100% metal, so excellent conductivity. Typically, they're made of aluminum or copper. They're plated for environmental reasons and oxidation, and so there's no non-conductive member in the whole system. And when we're using them in an I/O form factor, like in the bottom left picture or the bottom right picture, that thermal bridge is already pre-mounted onto the cage in an assembly. To make ease of implementation, you just press the cage into your system like you would any other I/O cage, and then you just apply your cooling solution to the top, and no springs, no force requirements. All you have to do is set your cooling solution at a compressed height, and you're done. So typically, it's as simple as standoffs or mounting your heatsink or cold plate or whatever it is, to your chassis. And this has been a productionized part on the market for several years now. We make it in a number of different form factors, mostly in the I/O space, but not exclusively. So if we look on the right side, oh yes, go ahead.
Going back on that, just a couple of quick questions. In terms of compressible mating cycles? Is that infinite or 10 or what?
Yeah. So, oh, that's actually on my next slide. So you got me
Oh,
on
right,
third
okay.
bullet, Alan. So it's wear resistant. So if you're actually rubbing against it, like using it as a wear surface to mate against, it'll go notably greater than 100 cycles for actual compression. If you're just compressing it and not wearing against it, then you're talking thousands, or I mean, we don't have a number, but nearly infinite, I'll say.
Okay, excellent. And you've got low thermal resistance. I presume that was a QSFP-DD case that you showed on the previous slide, was it?
Yes, I think that was, but in the bottom right-hand picture, you can see a QDD, a 1x4 QSFP,
Yeah,
and
I
an
guess
SFP.
just for reference, any
Yes.
chance you can give me a rough degree C per watt for that size of device on the
Sure.
QSFP-DD?
I'll let Alan chime in on what a QDD would be.
Yeah, for QDD, often they're applied with, as Alex said, they can be dry or greased. Often they're greased on the cold plate side or on the heatsink side. In that case, for QSFP-DD, the thermal resistance is about 0.6 to 0.7 degrees per watt.
0.6 to 0.7 degrees C per watt. Okay.
And that includes everything. That includes the interface resistance, the internal bridge resistance.
Is that both interfaces to that? This is just this device by itself, or to the actual heatsink and then to the air? I presume it's just this device, right?
No, that includes the interfaces also.
Oh, it's all the way to the air.
Correct. No, not to the air. Through the device, the contact into the device, through the device, and the contact out of the device, not including the resistance, the convective resistance if you're using a heat sink or something.
Okay, but it's the two thermal interfaces. So the actual physical interface of the top to the heatsink above is included in that 0.7.
That's correct.
Oh, nice. Okay, so both of them. Right. Okay. Okay, that's good. All right. I mean, this gives me a wet. I just need to do the math on the numbers for our use case. And this is the dimension of that is what, roughly what, 15 by 50 or something, or
a little bit smaller than that, but that's pretty close. Yeah.
all right. Okay. All right, carry on. Thank you.
Sure. So on the right side, this is, well, almost my last slide. So on the right side, there's a whole bunch of applications, and I guess Alan, you're going to talk about what is closest to.
Yeah, ours is
the
bottom right is basically ours.
Yeah. Okay, that's probably the most common, right? Liquid cooled cold plates interfacing, but there's a number of other spaces. What you saw, and I'll pull up what you saw at OFC, and I'll pull up a slide on it that I wasn't originally going to show. Is the direct to chassis conduction? A lot of people build systems that are fanless, and they need to get the heat out to the chassis, and thermal pads are common in that area, but thermal bridge is a lot more effective. So anyway, on the left hand side is sort of a rundown of the top advantages that thermal bridge brings over thermal pads, right? So the first thing is it's much lower thermal resistance, as you just went through the numbers with Alan, over a typical thermal pad, right? Notably lower, multiple X. Also, low and consistent compression force. So we've got integrated springs in the unit. It doesn't take a lot of force to compress it. We can actually tailor or tune the force to whatever we want through the spring design. And so there's no need for, extra hardware to bolt down your heatsink or your cold plate or whatever. We talked about wear resistancy and mating cycles. Right, it's completely elastic, so it doesn't take a set over time, right? Which means it's infinitely reusable. You don't have to replace the thermal bridge like you would a thermal pad, every time you service a system or open something up, or if it's just had too many mating cycles. It's all metal, so it can handle tough environmental conditions or temperature requirements. You don't have to worry about it outgassing or creeping with environmental concerns. Already talked about, simple hardware, right? So it gets rid of, those force springs that are typically used on heat sinks or clips or other, all that other hardware, and just, you can just mount your cooling solution directly to it. Large working range. A typical port like this one in these IO spaces are about 1 millimeter of working range. But if we're talking about bridges that are taller, we can increase that if we need a lot more tolerance in the compression axis. And so we talked about grease, right? You can grease those interfaces, one or both, to get better performance. And then last point is that, typically the bridge thickness, which is where a lot of people are interested in, like how much vertical space does this occupy? Typically in the 3 to 10 millimeter range, right? 3 for height constrained systems, 10 for large, tall gaps you're trying to fill with a lot of working range. But it completely varies in both X, Y, and Z dimension based on the application. We have nearly complete flexibility in sizing all the axes. Okay. So that was the end of the presentation. I did want to just pop up this one slide because I'm assuming this is what you saw, Alan.
It was,
at
yes.
OFC.
Yes.
Yeah. So for those who weren't there or haven't seen it, I'll just give a quick run through. So what we did was we took a remote radio unit, those boxes that sit up on cell towers and have all the downlinks for the antennas, which are fanless because who wants to climb a cell tower to replace a broken fan, right? So what the IO ports on those boxes do is they directly conduct their heat from the modules to this large fin stack that's part of the chassis. And so what we did was we implemented 4 different cooling solutions for the 4 different ports in the system, and we put in QSFP modules and we ran them at 5 watts, and we monitored the case temperature of each of the modules, which is the number that you see on the front. And so what we did for these 4 cooling solutions is from left to right. The first one, what we did was we brought the chassis or extended the chassis down into the port to hope to or try to touch the module or at least get close to the module. It doesn't offer any compliancy or any guarantee you're going to touch the module, but the goal was to get close, and it really has no additional componentry. Second solution is we just put a thermal pad directly on top of the IO cage, the QSFP cage, so the pad bridges between the cage and the chassis. And then the third one, we did actually like a riding metal heat spreader or heat slug, and then so that would take the wear of the module, and then we bridged that to the chassis with a thermal pad. And then the fourth solution all the way on the right is we put a thermal bridge. We used a thermal bridge cage. So the thermal bridge bridges between the module and the chassis to get the heat out. And so we just let the module go, let it get up to temp, and you can see that the thermal bridge module runs the coolest in this 5 watt setup. It was, it had a T rise of 7 degrees C over ambient, whereas the wear plate had a 15 degree T rise. The pad on cage was 35, and I don't know what you probably saw, Alan, but the direct to chassis one on the left varies pretty significantly from from day to day or use to use. In most cases it runs kind of somewhere in the middle. If you get some contact, it maybe only a 20 degree C rise, but if there's a gap that day, that can get pretty hot.
And that's a QSFP module, right? So
yeah, that was a QSFP module, correct.
That would be slightly smaller device, I guess, on a QSFP versus a DD.
I think the openings are similar. The DD might be a little bit longer.
Yes,
but
a little bit longer. That's right.
Either way,
okay.
Right. I mean, point made. Right. notable difference against other cooling solutions.
No, this is really good. In fact, while you've been talking, I've done some mental numbers in my head, and I think it hits the mark pretty well on what we need. So, all right, that's great.
Okay,
Any questions
great.
from anyone else? And I'll no, I love it. Congrats, guys. I do vaguely remember seeing it before and liking it, but I forgot when we've been talking about this. So I'm glad I bumped into you again.
Great. All right. Thank you.
All right. So what I'll do now is I'm going to share my screen, and I don't have a presentation, but I have my 3D models. So let me just. So I've been playing about with that. So hopefully I can, not as far along as I'd like to be, but hopefully it'll get the message across.
Aaron, I'm sorry I step in here. I noticed TE's presentation marked with confidential, but this is public sharing, right?
Yes. You understood?
Yes. Yeah. Yes, I understood that. So yes.
Okay, so it's not confidential, right?
Correct.
Okay, thank you.
Okay, let me just, I've been playing about this model a little bit, so let me just pencil things back together. So just going to need to get my bearings, put the wall in. So I'm going to, apologies for the regulars, I'm going to give a little bit of an overview for the new people on the call. I'll keep it relatively short. Okay, so we are working on a project which we call the High Performance Compute Module. And this is a single module. What we do is, if you know what's going on in our industry, you know, NVIDIA with their H100s and their new Blackwell, etc., and also the OAM module, the OCP accelerator module within OCP that AMD use and Intel use, you'll probably recognize the sort of the format in general. It's a physical module that's about 6 inches by 4 inches or thereabouts. But what we've done is we've been inspired by that, and we've looking at the way computing is going, with sort of being more data centric as well, and the energy required to move data around at these alarmingly high speeds that we need now. You know, obviously there's this trend of sucking everything inside the package for energy efficiency, etc. But there's little regard to outside. Well, I say that's unfair, but to outside the package, we have to step the bandwidths down tremendously, and there's desire to step them up considerably. And when we couple to things like storage and distant memory, we burn a whole lot of power getting to and from that. So what we've come up with, by the way, guys, I'll send you a link to an overview presentation I gave at OCP Global Summit. And at the regional summit in a couple of weeks, I'm going to be going into a little bit more detail, including this interconnect. I only have 15 minutes or less, so it'll be a very quick dive into these various aspects. But as we start to explore these a bit more, and we're putting a bit more meat on the bone. So essentially, you can see here. Let me just explain the water flow. So this piece here is what this bottom piece is this bottom piece is what we call the wall. And so there is no 19-inch racks. There's literally just walls. And on this wall, you bring facility power in, and then we get 48-volt power. You can just see those two pins there. That's a blind mate 48-volt power to bring 48 volts into the module, and we bring water in from the wall as well in these blind mate water connections. So without getting into too many details on that, that's how each module, and then basically modules are just literally tiled like Lego on the wall. There is no motherboard, because when you look at motherboards, they're now useless with these high-speed signals. Everybody's going to cables anyway, and the power planes aren't good enough to carry all the big power amounts without massive copper losses. So the motherboard's disappearing, and you can see that. You only got to look at Blackwell from GTC a couple of weeks ago, and you can see the trends are now well underway. Well, we forecasted these trends 3 years ago when we started this concept. And also we also forecast computing architecture needs in terms of ever insatiable amounts of data being closely coupled to the processor. So this basically is a PCB. Inside this PCB is your big powerful 1 kilowatt processor, and it's got basically a backplane on the back. So instead of plugging into a motherboard, it's a whole bunch of connectors, which I'll show you in a minute. And you can see in this example, we've got a bunch of E3.S modules plugged in. And also you can see in these channels, we've got 8 connectors that we call our topology interconnect for connecting the topology together, for wiring between modules in your needed. So this is very flexible. We can wire up any topology of any machine today, assuming the module exists with the chips that are available. We can configure a Grace Hopper, a Summit machine supercomputer or a Frontier supercomputer configuration. Assuming the device is coming in this module format, you could configure any existing hardware and software stack. But also you can innovate with new stacks as well. So this is a generic. So this is one building block for all, really. The E3.S module and the what we call the HPCM, the high performance compute module. Now let me just peel away the wall a moment, so we can see here the water and the power connections coming in. Let me just peel away the chip side. So this is actually, I should say, the water comes in here. This is a manifold. So the water literally runs down the veins of this manifold between all of these modules, all these connectors. And then the water pops up here and it comes into that lid I just removed. And basically we immersion cool, or we can immersion cool. We can do either a normal type of water heat sink here, and gap pad or thermal grease to the processor and in the power devices, etc. Or potentially we can actually do an immersion, a mini immersion chamber just on this side of the module. And University of Illinois has got some conformal coating techniques for this. So there's a couple of possibilities. Once the water's flown through the top lid, it returns back into the manifold here and then gets ejected out as hot water on this channel here. So essentially the cold water coming in flows over all of these pluggable devices first. So let me just unplug this media here. And you can see all of the E3 connectors in there at the moment. And let me just see if I can plug in. There we go. And so if you're familiar with the TA1002, I think a company called TE makes the cables for the EDSFF format. So you can see that we've got a little bit of a challenge here. The cables are clashing with so we've got these copper channels. So water is running through the base of these channels, but this would be a formed copper a manifold. And what we want to do is, we want to, let me just do my E3.S with a thermal interface. So what we were looking at, this is our thermal interface idea, a bit like an EMC connector. This is where you guys come in. And so we were thinking that what we could do is actually get some sort of spring-loaded mate and try and do this again with gap pad or whatever. And this is again just a cartoon concept, and I was asking for people to help us with this thermal interface. Essentially, one side is the path to the water to the manifold, and the other side is it might touch, but we're relying on one side. And in the E3.S modules, typically the big powerful, the processor or the controller will sit around here, so that will have a fairly good thermal path to the thermal interface. Likewise, we can put a thermal interface on this connector as well. And I don't think we hadn't done that. Now Z from Amphenol had done some examples in the and presented them. But so if this is a passive cable, we just need a passive cable design that can latch into here and be sort of pluggable and unpluggable. So we can either have media or memory, or we can have I/O, depending on our application needs. That's the idea here for this additional I/O. So if you're familiar with Grace Hopper, they have like 7 PCI bus lanes equivalent. So we could have like 7 of these slots just cabling to a neighboring module to have the same sort of bandwidth as Grace Hopper. But then you'd sacrifice your additional media. Essentially, there's 320 transceivers on all these connectors in here. So basically, that's what we need. We need a pluggable interface where we can get a thermal mate going on. And that's what we're working towards. Also, on the cables, if they were active cables, we'd want to obviously also cool the active device without again with some sort of thermal interface to the manifold. Back in here. So this is going to be new. I've built this wall here. This didn't used to exist, but somebody on a previous call did suggest that if we're trying to thermally mate against here, we need some robustness behind here to press against this and not break the connector off. So basically that's why I've put this in. So this is a recent ad that I've done this week. And so then these are topology interconnects. It could be passive copper, or they can be in active copper, like a retimer in the cable. Like, for instance, these PCI retimers that are now coming out. And I'll show you a bit on that in a moment. So they're in the region of 5 or 6 watts for 8 lanes. So it fits the wattage example that you gave. And then we can connect that, thermally mate that with the TE spring-loaded thing to the wall here. Sorry, it's to the wall here. And in fact, this gap, by the way, this gap to the, assuming the paddle card is here, this gap here is 5.6 millimeters. So, allowing for a processor chip to mate against, it looks like we would need like a 3 millimeter interface, assuming that then compresses to 2 millimeters, or 4 millimeter that could compress to 3 millimeters. I mean, so that looks like it will work with your heat spring. It looks like we're in the right region for that thermal mating. So, any questions on the thermal mating side of it? Does that make sense?
Yeah, it makes sense. And you just answered the question I was going to ask, which is what's that compressed height need to be? Certainly, if it's 3 millimeters.
Yeah, we may have a problem on this one.
Okay.
So this one, I was one. So I've been more concerned at the moment about the topology ones, but too many edges. So that distance there is 4.565 millimeters. So again, if you've got like a 2 millimeter, a 1.5 millimeter chip, you'd be okay. Oh, do you compress from 3 to 2, or is your compressed 3 millimeters minimum?
compressed is in the 2.5 to 3 range.
Okay,
Depending
so
on the
we're
performance you
right
need.
on the edge there. I mean, you know, if we have to do this, make it slightly wider, I guess we have to make it slightly wider. But
Yeah,
yeah, that
I think
was
I think the advantage that you have and could drive us down to the 2.5 range is you have a long area or long
yeah.
long
So on this
surface
one, we have a
interface.
really long area here, right?
Right.
And also, I'm not sure if we could design your thermal bridge into the lid where there's like a sprung piece of it, but the rest there's actually the remainder of the lid of the module. Obviously for the cables, it doesn't matter; it just finishes here. But anyway, we can have those discussions as to whether there's any practicality of making one side of your thermal spring, although it's a small area of the spring piece, there's a big area that becomes the lid of the E3S, is one solid piece, to give you thermal conduction from all the other gap padded devices to the spreader.
Yeah, and similarly, I was going to say, I think you have the flexibility to have the thermal bridge on either half of the interface. It can be on the modules and cables, or it can be already in place inside
Funny you
your.
should say that. Very well said. Let me just there we are. There's our thermal connectors. So here we are with our original design, and I thought, oh my, this is going to be an assembly nightmare and a serviceability. So if we had a wear problem, whereas what you could do is you could probably service if you had something wear out here, you could possibly replace this. And I thought if it wore out on here, and so I moved away from this to this. But like I say, either will work if everybody is happy that one is better than the other. Then we can go with I'd love to put it in here. It keeps these simple, right, and cheap.
Yeah, and I think most people would agree with that philosophy, right? All the module makers don't want to add cost and complexity to their module. They'd rather have it in the infrastructure. So
Right. So
yeah.
that would be a possibility. We could put it in design here. In fact, that could bring a whole horde of additional benefits as well, interestingly. Well, yes, it could and no, it couldn't. Right. Okay. Anyway, certainly worth further discussion. But you get the idea then. You see why I'm not excited about your product.
Yes, right. This is a perfect application for thermal bridge, right? You've got mating interfaces trying to pass large amounts of heat, and yeah.
So
you need that
my biggest
capacity.
concern has been the thermal model. I've always been saying we have no idea what our thermal interface could be here. Now, I believe that this is possibly at least, maybe it's a little bit narrower. So it might be similar size to the QSFP at the end of the day, area-wise. But let's just say it was a degree C per watt for talking's sake. We're saying we want to cool modules up to 40 watts. That would be the equivalent of a double width air-cooled E3.S. And but we would do it in a single width format because we could cool it. So 40 watts, if you're at that would mean we'd have a 40 degrees C rise, which isn't insignificant. But if the water, you're getting the cold water come in here, and so again, I don't know what, if the water was at 25 C, we would be running at 65, which again is well within reasonable tolerances of these silicon devices. So under a worst case scenario, that would be a 40 watt module, and a lot of these modules would be more in the 25 watt range. But yeah, so that was what we were hoping to do. So certainly from a penciling perspective, it doesn't look too drastic based on what you gave me. Okay. Anything else on that? Let me put it back together. All makes sense. Okay, so now if I just put this back together a minute, actually, let me put this. Yeah, let me put it back together. Do we need? We can just leave then. And now let me turn on. So what I've done here, actually, let me get rid of this. So here you can see, can I get rid of these modules? Just, oops. Wrong ones, sorry. Okay. Where is it? Okay, so you can see the board here with all the connectors. By the way, again, just for the new people, one of the things that Z looked at for us is because we're all on the back of a processor here, we can't have any through-hole connectors pins at all. So everything's turned into surface mount. Now, I'm just using models that have the through-hole stuff, but Z has done some work on showing what could be done for surface mount only. That obviously gives mechanical challenges, but because we've got the manifold, we're thinking you won't have these big forces of tearing the connector off the board because the manifold will protect it, and it'll just be an insertion ejection type force. So we're hoping that will be okay, but we don't want any through-hole features at all. So these topology connectors is where we've been thinking of this is what we're calling the universal interconnect. We start with an MC. We've had a few discussions around options, and without boring you with the details, we've said let's go with MCIO. We want to be able to go all the way from PCI Gen 5 type speeds, 32 gig, all the way up to 224. Now, possibly this connector design is not good enough for 224 in terms of a passive cable. But maybe when you went 224, you would have some active retimer copper cables, or even maybe some near package optics cables that could take 220 in and then convert them. But what we mean by universal is we want to do the entire range up to the highest speeds. We want to be able to do passive copper. We want to be able to do active copper. We want to be able to active optics. I won't call it photonics per se. Active optics, and basically we want to do a QSFP cage in a miniature format. The sad thing about where we are in our industry is we look at the latest NVIDIA module, and it's a relatively small module burning 1,000 watts of power. And then we look at a QSFP DD, and we've been migrating to OSFP. Is where we can barely do 20 watts in these huge cages, and you put like 8 cages together, and they're the same size. 8 times 20 is 160 watts, are the same size as a kilowatt processor. So the idea is can we shrink the QSFP down? So we're shrinking the system down as well as everybody shrinking everything into package. That's the whole idea of this. So we can minimize the energy for moving stuff around. And like maybe we can be in the 1 to 2 picojoule per bit for a processor talking to a media module without having to go through a PCI bus or something else and burn 7 to 10 picojoules per bit. Equally, if we want to do cables, then we can put retimers in the cables, etc. So this is this universal interconnect project that we're trying to do. So your thermal bridge could be a nice piece of that, because we need to bridge this universal interconnect into a manifold that is carrying water, because this is a direct water cooled only solution. So I've got 3 little examples here and these are slightly extended paddle cards compared to probably what's in the current standard MCIO. So they would need to be a little bit bigger. But what I've done is just a little space model. This here is a standard PCIe retimer footprint for a by 8 PCIe retimer, as in an Intel spec. So you can see the size of the paddle card, and you've got to, I guess you've got to attach your wires, your passive wires up here. We could put possibly some power and EEPROMs on the back, but we'd need the thermal mate to actually mount onto here. And what I should do is, just while I'm there, because you've not seen that part of it. In my PCB, simple MCIO connector. Oh, no, not simple MCIO. Didn't delete it. There we go. There we go. So these are the Amphenol ones. They're just a 3D model, and I just showed an example there of a copper plate. So you can see that would be mounted in this, and mate to the chip, and then this would be connecting to the body of the thermal manifold. So this is where your silicon, your thermal bridge would come in here. So that was my little mock-up of an equivalent to a thermal bridge. With just again a cartoon to get the concept across. So that thermal bridge would be mounted onto this chip, and it would be all packaged into the cable, and we'd have ourselves or we could put the thermal bridge, I guess, like you said, in the actual manifold itself, and then the cable would just have a clean piece of metal interfacing to this chip. So that would be that might introduce another thermal interface. So we're thinking that this is in the 5 to 10 watt region. These would be is what we're saying. So again, that would be a 10 degrees C rise for 10 watts well, maybe a bit more because it's a smaller area. But we'd want a good thermal mate to the big chip. So that's using MCIO. Now, by the way, guys, just so you know, the MCIO, we've actually redefined the pins as well, so that we can bring power on, and we have much more modern, shall we say, sidebands using something called LTPI, and so we can carry that across the differential pair. So we might need a little CPLD device on here as well to bridge some of these I/O signals. And then we'd bring 12 volt power in here as well, and you'd need some PMIX to actually step that down to this. So obviously I've not shown any of that. I think we should be okay, but maybe we need to extend the power card a little bit more. I don't know. But this is with and I think there's some retimers as well for Ethernet. So if we were doing, because it's universal interconnect, this could be Ethernet, PCI, it could be NVLink, Infinity Fabric, etc. And so that if it was active, it would be dictated by what retimer you put down. Then what we've got is we've got an optics version. So Avicenna, I'm not sure if you've heard of these guys, but they've got an LED type optics solution, which really looks quite interesting. And they gave me some 3D models of what they've got. So again, you need to take this with a large grain of salt. This is just a cartoon idea. Is if we had their chip and it was flipped over on one side, we could connect this to the cold plate. And then this is a ferrule that would be mated. So let me just expand this. And if we just take that ferrule off, so that was a pluggable ferrule inside here, but you can see in this, so this is a hole through the board. And again, I'm not saying this is the way it's going to be done, but this is their MT ferrule where gives them the alignment. The nice thing about their technology is they need about 5 microns of alignment, which they say is easy to do mechanically, unlike some of the single mode fiber stuff and the silicon photonic stuff. And then they have a big array of LEDs where they shine down a multi-light pipe. So their chip would be on the other side of the board. It would be shining through, and then we would mate to put that back on. Then you would plug this in, and this would be part of the manufacturing process of the connector. and then a really fine optical pigtail would come out the top of here instead of the copper variant. So now this is the way they've done the. I'm not sure of the corner turn requirements of these optical fibers, but so we see that this is breaching this cage width here, which again I think our current design has a little bit more space, so it may actually just squeeze in there. I haven't had a chance to try that, but we would need some sort of ability to do the corner turn here if we implemented it like this. So this would be an active optical solution. And the thing is, look how tiny their device is compared to the big retimer chips for the active copper. And obviously any power supply, etc., paraphernalia around that we need to power that device as well. So that's an active optical. And that would there is an example. And I've spoken to the likes of Ayer, etc. In terms of what I could understand from what the booth at OFC is they don't have, and that you might be able to say, but they don't have PHYs, traditional PHYs. I think they do more advanced packaging interconnect variants. So that wouldn't work for this, I guess, because we need traditional transceiver PHYs. Also, we would need, if we did it this way, we'd want silicon photonics to have the optics coming out the back rather than out the top or out the side. And I'm told that that's possible, but nobody will say whether they're doing it or not, or whether it's a good idea. But if we had optics at the bottom of the silicon photonics, then we could do something similar to this. Okay, that's that. And so, like I said, they do 1 terabit. Avicenna do 1 terabit per second per fiber. So that's a total of 2 terabits per second for one of these, which is not bad. And so therefore it can keep up with your optics. Our 800 gigs optics is in both directions, right? I think they're making an 800 gig optic module using QSFP. So we could potentially transfer their QSFP design into this format as a sort of a show and tell, a POC. Then we have this co-packaged option, right? So the idea here is this universal interconnect could give us a graceful path to co-packaged optics. And whilst in a co-packaged optics scenario, we lose all of the copper pins, I was thinking if we had a sort of a universal sort of body where it could be converted into a pure optical solution, then that would be attractive. And those of you that remember Intel, when they did the original USB, they had a couple of holes in the back of it where you could put passive optical versions of USB. It never took off, but they only ever did the electrical one. But it's the same sort of concept. So the same mechanical body that could carry a passive optical, and then we could plug that into this module like so, and you would just mount a different connector that was the same sort of body format. So if I go back to this.
Question on that last one, Alan. And no, I
Yes.
don't remember the original USB. That's interesting history I didn't know.
Yes.
Is there an interference with where the pins or pads on the board would be with where you want to pass that optical interface?
Yeah, so again, very good question. So my entire real point here is it's not that we'd support one or the other. So if you're making a module here and you're putting the co-packaged optics down, you actually wouldn't bother soldering that. You just solder a similar sized body. A similar, the connector and the latching and everything would be the same, but you'd put a passive optical cable into it.
Got it.
The design of the passive optics, it would carry these 4 pairs of fibers, and you'd need a sort of a little alignment. And so it need to be a bit of slop in these so that they could nicely align with each of these different co-packaged ferrule holes. So
but you can make a connector body that essentially does that.
Yeah, effectively the connector, the sympathy of the connector body is common throughout the other free designs. The passive, the active copper, active optical, but it doesn't have any pins in it at all, apart from soldering it down, surface mount to hold it in place, and then leaving the clearances. As you will see in a moment, I've done it very crudely. Does that help?
Yes, thank you.
Lost my. Where did it go? Oh, apologies. I've run over time here. Is everybody okay? I lost. Okay. So let me. Why can I not? Can't find this. This normally pops up. Ah, there it is. Right. There we go. So I've translated it to here. So the same sort of setup, yeah. But what I've done is if I get rid of. I just hide those. Okay, so you can see that. See the connector?
Yep.
So all
Yep,
the
I
pins
see
have
what you've done.
But I've got the holes down. So the body is essentially the same. It's showing these pins, but they wouldn't necessarily exist. Only sort of mechanical versions of them. And then if I take this lid off, there we go. And then I flip here. So then you see here are the actual co-packaged optics devices. It can be so this would become a substrate, and then it could electrically wire to the to the substrate chip. So this is where positioning of these, if they're regular PHYs, that'd be fine. But if you wanted to be chiplet type I/O with half a picojoule per bit, you might need to, your processors or buffer chips would need to be closer to this. But you see these optics, these converters. So this is an organic substrate sympathetic co-packaged optics approach. And again, it's completely cartoon. It's completely impractical. It's just trying to show the thought process for the experts to say that'll never work, or yes, we could make it work, but not like that, And that's basically. So that's basically what I've been doing, and that's what we mean by universal interconnect. So maybe to bring it back to a presentation. Oh, this is my not that presentation. Bring it back to presentation. Nope. Let me just do file. Recent. Yeah, so this was our inaugural meeting for this little work group. I did this presentation. And so, wait a minute. Yeah, so this is what we turned into the universal interconnect. So again, we were looking at Samtec's Accelerate and Molex's Nearstack because they were direct to pin, but we wanted the paddle card. And MCIO is prolific, so we ended up choosing this one.
Did you, just curious, did you also look at OSFP?
OSFP. No, because it's huge, right?
What's the...
These are the
Let me
near...
check the thickness of the OSFP is definitely much thicker than MCIO, that's for sure.
Oh, paddle card wise, you mean? Paddle card thickness?
Yeah, paddle card wise. The connectors, well, if we're gonna set it vertically, the...
Yes. Yeah, I'm talking vertical, right? A vertical OSFP.
Okay, let me see if we can.
I mean,
well, so I mean,
because
I guess I did look at the TA1002, which is similar to MCIO, right, but with the extra key in, but it was too big a connector to get 8 of them into the format.
Do you know what the pin pitch is on MCIO? I don't know it that well.
0.6-ish, I think.
See, I think OSFP is also 0.6.
Do they do them in these
two-row.
little internal formats, or anyway?
We do them in a vertical format. So anyway, go ahead. Sorry,
I just thought OSFP was a huge cage. That was all. We don't want a
right,
huge
but
cage.
we don't. Right, but we don't. Cage is unimportant. It's
Okay,
the
fair
connector
enough.
that's the.
So anyway, so this slide is really to say this is turned into a universal interconnect. So protocol agnostic, like I said, we got to deal with the bloody impedance considerations, especially when we get to 224. I don't know if this sort of middle of the ground 92 it works for that or not. And then we've got by 8, so we're gonna have 8 transceiver lanes. Hopefully we could go to 224. Sidebands, we go to this tunneling over LTPI, which is LVDS tunneling protocol, I believe, stands for, plus some clocks, and maybe we have one static cable present pin, so we know a cable's plugged in. Then we have for active cables, chiplet retimers, silicon photonics in the region of 5 watts. We have 12-volt power pins and paddle card support for active components, as we talked about. So that's a total of 66 pins, and I just took a quick stab at. So I think there's 74 pins on the MCIO. So I just took a quick stab at the pin out. It just is a starter for 10. Okay, and then we talked about, I went through all this today, showing you these things. And that this also talks about the through hole challenges that we need to get over. So that was in our first presentation at this meeting. Okay, guys, that's basically it. Hopefully you've got a good feeling.
Yeah, I appreciate it. That was really helpful, Alan, especially for us first timers.
Yeah, so to be clear, right, we're a work group. We've been in this concept stage for 3 years. I've actually done a presentation in my I did do a presentation last week where I looked at Blackwell. I looked at NVIDIA's GTC Blackwell keynote, and I did a presentation as to why you can see the shift that they're all making, that shows that what we're doing here and have been doing for 3 years, we had the foresight to see where the industry was going to go. And we said, if you start from a clean sheet of paper, where could you be? The reality is we are so crazy in our ideas that we can't really, there's nobody throwing money at us to do this. But we are trying to get some funding from the DOE Oak Ridge National Labs New Frontiers RFP, which hasn't fully come out yet. And so we've been trying to pull a proposal together. And in that proposal, there's 3 sections. There's one on power and thermal. There's one on system management, which is another aspect of these modular systems. We need to revamp the system management and the control plane to be much more advanced. So we've got a separate group on that. And then we've got this universal interconnect one saying we want, instead of this sort of breaker switch over to co-packaged optics tomorrow, we've got this elegant traversal. So the same basic system architecture can support this migration from passive copper to active optics to co-packaged optics. And that's the idea of the universal interconnect. It all speeds. And by the way, that universal, so the co-packaged version I just shown you with 4 of the Avicenna optical is 1 terabyte per connector. So we would have 8 terabytes per second of I/O bandwidth off this module, which is HBM type bandwidths across our network. So we're fairly future-proof in terms of and the concept is not that hard to build if somebody had the money to build it and wanted to do it. And when you see what they're doing with Blackwell, with all the cabling and all of the water cooling, what we're doing here seems to make more and more sense. At least it does to me. In OCP, we are talking about where do we go next with OEM, and ideally, I'd like us to go down this route with OEM. But again, just to put the sanity on it, guys, we don't have anyone throwing a ton of money at us right now. Okay.
Okay. Well, when you're ready to build and you want to get some thermal bridges, we'll work with you to size
Well,
them,
so
build them,
yeah.
and all of that.
Well, that said, you know, it's like everything in this DOE proposal. We're trying to put an attractive proposal that suddenly people say, "Oh my God, that could work." And you know, I think your thermal bridge is one of the missing parts. So we're an open, you know, we're trying to develop an open interconnect here. MCIO, I guess, is co-licensed from Amphenol. You said to me that you co-license your thermal bridge. If we can design this connector together, at least in some sort of beyond Alan's cartoons, and maybe start to get the basics of a spec, so that if we can put it in the proposal to the DOE, the way we'd like to structure this proposal is that DOE could say, we like the whole project, we'll fund the whole thing to a POC, or actually that universal interconnect piece looks very interesting by itself, but we'll just fund that. We don't like necessarily the rest of it, or we'll just fund the power and thermal piece or the system management piece, but hopefully they fund all of it. And so it brings it to a reality. But you know, that's what we're hoping. So I'm not sure how many of you have worked in OCP before, but the whole idea in OCP is we work as an open community, trying to pull these pieces together to make, you know, so that we've got an open format that can then get widely adopted. That's the desire. So if you can spare some volunteer time and keep joining us, and maybe start to work with on the specification and maybe more attractive 3D models showing off your tech in the MCIO format. If you've got other ideas on other formats where you can do the whole shebang, happy to hear. Again, with us, we need again those people that you guys are pretty good. You have your RAND licensing, so I guess that works, right? So as long as OCP sees a level of openness for the industry, you know, that's what we've got to do, is we've got to have some level of openness to make this work. Otherwise, it just becomes another proprietary standard that no one will adopt. So, all right.
Yep. I mean, that's all above my level. So I don't, you know, I have not been involved much in OCP. I don't really know how any of the licensing stuff works. So
yeah, I guess that's where who was the other chap that took over from Chris Blackburn?
Josh?
Josh. Yeah, so that's where I hope that maybe Josh can make a few calls in terms of so I did copy Josh. So I don't know if you spoke to Josh, Terry.
I did. Well, not after the trade show, but like, so the current situation with the thermal bridge is that we are indeed actively looking for, we are building a candidate pools that we can select from to start a communication on the basically second source licensing or through any other business partnership means that can have this technology being provided by outside of the TE source. So that is ongoing at the moment. It's not, and it's not just for this OCP program, it's for a lot of other customers' requirement that they want to utilize and they want to adopt this component. And then we're putting everything together. And then my current outgoing projection on the timeline for the second source is we will probably have some sort of partnership established by 2025.
Okay, look, I think these are sort of the aspects of the spec that we need to deal with, right? But like I say, you connector guys seem to work well with the OCP with your RAND agreements. It seems like you've had various traction with that sort of stuff, or these other agreements, you know. So as long as there's that, as long as you can only buy it from us and nobody else, then basically we're probably hosed in terms of being OCP. But
I understand. Yes.
So So yeah, but if Josh can pick up from that, and Josh can maybe get some engineering effort to you know, and you can bring ideas. The thing is, as long as you're prepared to share them, you can bring ideas like your OSFP connector example if you think that's a better approach to this. I mean, we've had several discussions on this where MCIO seems to make sense, and this obviously is prolific as a connector, so and it's prolifically licensed already. So but yeah, I mean, we're at the end of the day, where we're at right now is he who puts the most effort in, if we get any traction, is most likely to come out with a you know, with the standard, as all these things, right? I'm sure as soon as money appears, everybody will be more than keen to work like crazy on it. You know, if Intel said they were going to adopt it, then suddenly but that's typically too late if you want to be the chosen one. So I don't know. It's an open community. So basically that's where we're at. But I don't want to kid anybody that we've got people knocking down the door for this yet. But hopefully the message carries across that we have something interesting going on here, and it's becoming more and more relevant with every day that you see what's coming out of the proprietary guys.
Okay.
All right. Okay. Well, thanks, guys.
And
good.
Alan, I did see several of your projects conceptual presentation. Would it be available online, or after the meeting? Can you share that with us?
Yeah. So it's basically, if you search for OCP HPC Wiki,
okay,
you'll find our webpage where all the previous recordings and there is an overview presentation from. And I can. Yeah, basically search for OCP HPC Wiki I can
okay.
I'll send a mail out to the group just to give you a link to it.
Okay, thank you.
Okay. All right, guys. Well, thank you very much.
All right.
Thank you.
Thank you very
Thanks,
much.
Alan.
Bye.
Take care. Bye.